So a very good morning to all of you. So today I'll talk about jets, one of the most important QCD observables in both hadronic, leptonic, hadronic, and let's say heavy ion collisions. So the idea would be to introduce jets and talk a bit about the jet algorithms, which are quite popular or currently being widely used at LHC energies. And then we'll also talk about the heavy ion aspect of jets. So in that sense, I will talk about dijets and dijet asymmetry. Most of the contents are taken from slides of Professor Salam Gavin and Matteo Cacciari because they are one of the authors of the fast-jet code, and the explanations were quite good. So let's start. What are jets? So for last 2 days, we are also talking about the physics of, let's say, quantum chromodynamics with the involvement of protons, quarks, and gluons. So all these high energy protons like quarks and gluons, which are produced in the initial state of, let's say, hadronic collisions, give us a playground to test the theory of QCD. But however, it's not possible to observe these quarks and gluons because of the color confinement, and what we observe at detectors are collimated spray of hadrons. Now, jets are essentially the collimated spray of hadrons that result from fragmentation of a high energy quark or gluon, because these are produced very early in the collisions and they immediately branch and immediately fragment to hadrons. So when you observe at your detectors, you don't see quarks and gluons, but you see spray of hadrons that result from the fragmentation. And these are essentially, therefore, we can treat them as proton proxies. Now, the study of jets dates back to, let's say, 1970s, where gluon discovery happened. So at that time, QCD was proposed as a candidate for the theory of strong interaction. So it was open for testing. And then we have this data from the E plus E minus collisions at Petra, where your E plus E minus can collide and they can interact electromagnetically to give you a quark anti-quark pair. So we were expecting a dijet sort of structure, but what was observed, like this sort of structure. So you have 3 jets, okay? So 3 collimated sprays of particles carrying large angular momentum, and they had significant number of events which could see such characteristics, and by these results it was conclusively established that QCD is indeed a theory of strong interaction because gluons were discovered. So the idea was that one of the quark or anti-quark could branch to give a gluon, and that could seed the third jet. So jets can be viewed as proxies of initial protons, and from then onwards, lot of studies in experimental physics were carried out to study jets, and from them to know about the initial scattering. Now, why jets? So this is clear. By measuring their energy and direction, one can approach the idea of the original proton that produced them. But this is not the only reason. We'll see that the jets are used for many searches because they act as a perfect background for, let's say, Higgs searches or BSM searches. So they are everywhere, and one should be very careful while defining jets and doing the analysis. Now let's see how the shape of the jets are generated. So as strong interaction has asymptotic freedom, that is, at higher energy range, your strong interaction coupling constant becomes weak, and because of that, your quarks or gluons for a while can have enjoyed their individuality, so they branch into small protons until the strong force sets in and they are forced to hadronize. So if you see a quark of very high momentum or high energy, so it can radiate a gluon, and QCD states that this radiation of soft gluons is enhanced compared to large wide-angle gluons. Now, this probability of gluon emission is given by this expression. So, if you consider on this E and theta dependence, you can see that, so if you emit a gluon with very small momentum or what you call as soft gluon, then it diverges. This is known as infrared divergence. And if the gluon is emitted very close to the original parton so that the theta is extremely small, then also you will have collinear divergence. So when you calculate using TQCD jet observables like rate of jet production and all that, one should be very careful about taking into account these divergences. Now, once we see that these quarks and gluons, they keep on branching and emit gluons till you reach when the virtualities become low and they are forced to hadronize into hadrons. So just because of the structure of perturbative QCD, you see that they keep on the high momentum initial quark and gluon, they keep on emitting soft gluons till and at small angles, so that beam is originally collimated at the parton level, and once they hadronize, once that beam hadronizes into the hadrons, you see it as a collimated spray in your detectors. This also tells that why your gluon emission probability is high when your quark or gluon fragment or branch into gluons. Now, if this is true, then how do you define jets when you do the experimental analysis of data? So, if you see that you have two partons, and then this is the next to leading order emission, and then your parton shower, the QCD shower, and then this is the thing which you observe at, let's say, hadronic level. Now, all of these should give you two jets because originally you have these two partons. Okay. So this sets the idea of defining jets for experimental analysis, which should be resilient to this QCD effects, because these three diagrams, let's say, show different aspect of corrections in QCD. So, but one should realize these three diagrams basically, or let's say these three diagrams really basically start from two partons. So when you do the calculations of jets, this should give two jets when you do your jet rate calculation. So the idea is to say that whenever you define a jet or you define a jet algorithm, that should be resilient to these QCD effects. So a jet definition is fully specified set of rules for projecting information from an event's partons and hadrons onto a handful of parton-like objects. So we have to project this initial state thing into calculable or measurable objects known as jets. Now for this, you have to identify jets so that you can start to make a setup of rules. So if you see this structure in your detector display, so how many jets you see? How many jets? It's clearly two. Okay. So one can define certain rules so that you can able to really cluster these particles, because these are hadrons or tracks. So you can cluster to generate two jets, and you can associate those two jets to the initial partons. Okay. Now here, how many jets you see? Okay. So you can have three jets. So your algorithm can decide on having, let's say, three cones, and you can get three jets. But let's say someone else also can treat this as four jets, right? So depending on the algorithm, you can also get four jets. Okay. So one should be careful. And this visual, let's say, visual picture is not always easy, specifically when you have, let's say, high multiplicity in your event jets, in your events like this, or in heavy ion collisions like this. So it becomes really impossible to see any jets here. So in those cases, it is important to have jet algorithms with certain rules so that you can identify or classify jets. So what does these algorithms do? A jet algorithm identifies the jet in an event measure their form momentum, and thus maps the momenta of the final state particles into momenta of a certain number of jets, because this is what we measure. We can measure in our experiments, and then you implement the jet algorithms, and that will give you a certain number of jets with associated momenta. Okay, so this is the picture. This is your initial partons, then you have your, they hadronize, and then, so this is the true jets, but then you have detectors, and then you have to reconstruct, and these detectors will give you the information of the tracks which you measure, and from those tracks you reconstruct jets and then try to map them into true jets, which would give information about your initial partons. So there's a standard way of defining jets, certain set of rules, which is also known as accord. So the rules are, let's say, both for theory and experiment, your jet algorithms or definition should be such that they should be simple to implement in an experimental analysis, and they should be simple to implement in theoretical calculations, because as you see, there are complicated objects really emanating from a complicated branching process, which we are not, let's say, which we don't see. So they should be defined at any order of perturbation theory. So there should be, the divergences should be taken into account, and yield finite cross section at any order of perturbation theory. And yields a cross section that is relatively insensitive to hadronization. Okay. So then there comes the concept of infrared and collinear safety, and this I talked about when you let's say, like any other quantum field theory, your QCD also suffers from these divergences. So, but in experimental data, how do you define these divergences, or what do we mean when we say that your algorithm is, let's say, IC safe? So it means that if one modifies an event by a collinear splitting or an addition of a soft emission, the set of hard jets that are found in the event should remain unchanged. So let's say you have added here one thing, like it's a collinear, let's say it's a soft emission. So then the algorithm should give you the exact same number of jets as it was earlier, like Pn. And if you really emit another collinear emission is there, or addition of a particle, I'll show you how it works, then also it should be resilient to that. So if we wish to able to calculate the jet rate in perturbative QCD, the jet algorithm, what we use should be IRC safe, because then we'll be able to, let's say, compare the theoretical predictions with experimental measurements. This is the PTR shower of, let's say, gluonic shower, and then the branching happens, still the energies are low, so that you can't have, let's say, further branching. So what these algorithms do, so in experiments you observe particles, here hadrons, and then you sequentially combine or cluster these particles to arrive at a jet. So it's the bottom-up approach. So there are two sets of jet algorithm approaches. One is cone algorithm and the one is sequential clustering algorithm. So what this algorithm, and this was used, I mean, when the jet analysis was started, these were the most widely used algorithms, but now most of the analysis in CMS or at LHC energies, they use the sequential clustering algorithms, which really, let's say, which really tries to mimic the QCD branching and then tries to cluster it from the bottom to get the original jet. Now let's talk about the cone algorithms. This, let's say, this works on the basis that jet carries the maximum energy. So you find regions in your, let's say, event where a lot of energy flows, okay? And then you try to cluster your particles, and here there are also 2-3 ways where you try to cluster the particles, or let's say particles with certain momenta depending upon their eta phi distribution. So I'll show you examples of these two algorithms to see how jets are reconstructed via these two approaches. And under cone algorithms, there are also many, let's say, many subsets like, iterative cone, then cis cone. This all depends upon how the seed is designed, or let's say defined, and whether the splitting and merging of the jets, let's say jets defined from stable cones are carried out. And some of them, most of them are not IR safe, barring cis cone. And the advantages here is that all the KT, anti-KT and CA algorithms, all of them are, let's say, IR safe. Now what happens in a cone iteration? So the idea is to find stable cones. So how do you define a stable cone? So first you define a radius depending upon the rapidity and azimuthal angle of the particle distribution. So that will give you the idea of what sort of jet you want to form. So this is the input parameter. This is something which you have to decide when you start your cone iteration. So let's see, so the idea is these are like through particles. This is, let's say, rapidity, assuming that phi is 0 here just for the sake of simplicity, and the height tells us about the magnitude of PT. Okay, so now so it's based on the let's say it's based on the idea is that you have to select where the highest, let's say, energy flows. So you take a particle, or let's say the particle having the highest momentum. So this becomes the seed of your cone. Okay, so you select this. So this is also the axis of your cone. Now depending upon your R, radius of the cone, you define your cone. Okay, now inside this cone, because of the radius, you can have all these particles. Now we have to see whether it's a stable cone or not. So now add up the momentum add up the momenta of all these three particles and see whether the combined momenta is equal to the seed momenta. Okay, if it is, then it's a stable cone and you assign it as the jet you have found. So if you see that, since this particle has a higher momenta than this, so the combined momenta of these three particles lies here. So this becomes your new seed. So if it becomes your new seed, then you have to define the cone with the same R, but the axis or the new seed should be this dashed line. So if this is the new seed, okay, if this is the new seed, then you see again within that radius you all have these three particles, and the combined momenta of these three particles also, let's say, matches with the new seed. Then you really say that this is a jet, and you perform, and after you find a jet, you remove all these particles and then try to find the stable cone for all other particles in the event. This is a simple example where I'm not showing the other particles, but this is the iterative, or let's say iterative cone procedure where you remove the particles once you find the stable cones, and then you jump to the other particles in the event. So now let's see the PT. It is not PT as such, it is not a collinear safe observable. So here your PT can, let's say, if it, let's say, branches, or if that high PT particle, let's say, branches into two particles having, let's say, this PT, then we should see that whether you are getting the same number of jet or not. So now we have 4 particles in the event. So now you have to select the leading particle, which should be this. So that should be the seed of your cone. Because if you see this, due to the splitting of this particle, this, let's say, this used to be the original seed. Now the particle splitted into 2 particles of intermediate PT. So now the seed changed for the same event. Okay. So now this becomes your cone seed, and using that same diameter, you try to put your cone. Okay. Now you see that this particle is excluded, which was not the case in the former which is not the case in the former seed. So now this is the thing. Now you have 3 particles inside, then calculate, or let the sum all the 4 momenta, and then you see that the new momenta lies here, so you have to shift. This is not agreeing, so this total new momenta is not agreeing with the original seed. So you have to now shift the axis, or this becomes your new seed for the cone. So you shift it around that thing, and now again you have only 3 particles, the same number of particles, and also the combined momenta of the same of all these particles agrees with this seed. So now this should be your jet. Okay, this is your jet 1. So now you have this particle remaining. So once your jet is defined, so the idea is you remove all these particles. Okay, so you don't have to consider this particle. Now you have this particle remaining in the event. So this is the only particle, so this becomes your new seed, and you define your cone here. Okay, your stable cone here. Now this will be your new jet because there are no particles around. So this is gray in color, that means they don't exist anymore. So this becomes your second jet. So due to your splitting of the high momentum particle, for the same event you are getting now 2 jets. So this shows that, this was just an example to show that this finding of stable cone is not IR safe. So now resort to the sequential combination algorithm, which is, like I earlier said, is a bottom-up approach. So once you know that, you start your branching from the initial quark or gluon, and they branch emitting gluons, and at some point they'll hadronize to give you collimated hadrons. So in this sequential branching approach, what is done is that you, from the hadrons, you try to cluster the hadrons and keep on adding their momentum till you arrive at the original jet. So here the inputs you have 2 things. One is you have to decide what should be the minimum PT of your jet. Since they are high energetic particles, normally the transverse momentum is kept very high. It's like greater than 20 GeV or something. And then you have to decide the jet radius R, which is again defined in, let's say you calculate the delta R within which you would like to cluster your particles, and this is defined in a similar way the cone radius was defined, and you give a value. You can give 0.4, 0.5. So when you see jet analysis, you see jet calculation with different values of R. So what is done here, you have 3 sort of algorithms here, KT, anti-KT and CA algorithm. So this also calculates the, so once you have a final set of hadrons, you calculate the distance between the particles. Okay, this is given by this. So distance means in terms of y and let's say rapidity and azimuthal angle, and this you do for all the particles in the events. Okay, then you also calculate the distance of all the particles with respect to the beam axis, and this you define like this. Now find the smallest between the calculated DIJs and the DIBs. So if you find the smallest one to be DIB, then treat that DIB or that ith particle as a single jet and remove from the calculation. Now if you find Dij to be let's say as the smallest distance, depending upon what values you get here, then combine the particles, 2 particles I and J within that cluster to give you the total jet momentum, and then you treat that jet as not jet, let's say you treat that object which has a total momentum of ith and jth particle as another particle, and again do the same thing. So if Ij, recombine them, so add their momentum, else call I a jet and remove from the list of particles. Okay, repeat the procedure till no particles are left, and use jet with certain PT which depends upon the analyzer. Okay, so normally high PTs are chosen. So let's see, and in anti-KT algorithm it is exactly similar to this algorithm. The only thing is that instead of minimum of this, you try to take maximum of this. That means it first chooses a hard particle to start with. Here it doesn't do that, it doesn't see whether it's hard and soft, it just sees the distance between them. But in anti-KT algorithm, because it is 1 by PTI square. So it actually chooses the hard particle and then exactly follows the same procedure. So the clustering here or the recombination grows around the hard core. Okay, and in CA algorithm, it's just minimum, it just recombine pairs close in delta R. Okay, so this thing is not actually there. So you just see the delta R value and whatever particles are there, just recombine them. Okay. Now see let's see how this functions for the KT algorithm, and it functions similarly for the anti-KT also, but you will see what is the difference when you get the jets. So let's see, this is an event and these are the number of particles having certain momenta, the height will tell you the magnitude. So then you start calculating the distances. So you calculate with respect to all the particles. Now suppose here you can see that this distance is small. So you pick these two particles. So once you find the smallest Dij, then the recipe was, then you combine these two particles. Okay. So I have combined these two particles. Now this is the new object, which we don't say a particle, but you treat it as a particle. Okay, because you have to find all the clusters inside that value of R, which is chosen by you. It can be 0.4, 0.8, whatever. Now then you again calculate the Dijs treating this object as a particle, and suppose you find the minimum between this and this. So you found that the Dij is minimum for these two particles. Then what you do, you again recombine them, right? So you recombine them to get this PT, and then again you keep on repeating this procedure, okay? And you will keep on repeating till they should all fall within that same R what you have, let's say what you have decided on. If the distance increases, then you don't cluster, okay? So if you continue doing this procedure, you finally get like these two jets, and these are well separated, okay? So the Dij is higher than what is given by the expression. So from all these particles, you could able to generate two jets, and this is what and the momenta is also given for the jets. Then you say, okay, in that event, I could reconstruct two jets. Similar thing also you have to do for anti-KT algorithm. The only difference is that there the cluster grows around a hard particle. Okay, so these are the clusters, the shape of the cluster, jet shape, which you get for different algorithms. And you see the good thing about the anti-KT algorithm and why it is popular, rather it is the default algorithm nowadays for jet reconstruction, is that it gives you circular jets, because you start from a hard particle and then the clustering develops around that. While for, let's say, KT, which is here for a certain R, you see that you don't have any control. It depends upon the distance you get. So you have irregular jets, and that also happens for CA because it doesn't consider PT at all. It only considers the delta R and see whatever particles are inside that region. It tries to combine them to get the, although you will get most of them, if you see the performance in simulations, you get more or less similar number of jets, but these are popular because first of all the jet shapes are quite regular. So when you do efficiency and acceptance corrections, or when you do the linearity study, this algorithm scores well. It becomes easy for the analyzer to do the corrections. Therefore, anti-KT algorithm is currently the default algorithm compared to this. But it also depends upon the type of analysis you are doing. Like if you are looking for, let's say, jet substructure. So it can happen that two jets are extremely close to each other. In that case, the anti-KT might identify them as one jet. So in that case, KT becomes important. So depending upon what analysis you are doing, you have to choose your algorithm. Okay. And these are the recent results from CMS experiment on jet reconstruction. So this is just to show that using different, let's say it's written here what R they have chosen and what algorithm they have used. So this is the jet cross section for, let's say, PP collisions at 7 TeV, and you can see that it has excellent agreement with the PQCD estimations. So as I mentioned, and these are the reasons why we are why we want to do jet analysis, because literally you can see jet analysis is everywhere. It's beyond standard model physics. They are helpful, Higgs physics, because they act as a big QCD background. So it helps when you do analysis and then you try to constrain the cross sections. So those are the input to many Monte Carlo generators. It helps in tuning of the generators and a lot of things. And with LHC, this number still grows on. Okay, but as I mentioned earlier, we have to see how jets behave in heavy ions, because all these all these estimations and measurements are done in PP collisions or PP bar collisions or EP collisions, where you don't have a medium. Okay, so the prelude to jets in heavy ions comes really from this very nice paper, where it's written that high energy quarks and gluons propagating, now they are not propagating through vacuum but through a matter. So quarks and gluons propagating through quark-gluon plasma suffer differential energy loss via scattering from quarks in the plasma. So this is something known as jet quenching. So this makes jet in heavy ions very interesting and challenging. Challenging because you have a lot of particles produced in the final state. So it becomes challenging to reconstruct jets, okay, because you have a lot of background. But it's interesting because once jets pass through this medium, they lose energy, they give us information about the partonic energy loss. Okay, so the partons crossing the medium lose energy via scattering, and as well as from gluon Bremsstrahlung along, so they lose energy, so they give us information about the partonic energy loss. And so analyzing jets will tell you how do parton showers in hot medium differ from those in vacuum. So this will give you important results which would help us to understand the QCD in heavy ion collisions. So let's say till few years back, we had this indirect observation of jet quenching. Let's say we started to tell them as jet quenching, but we never used jets to study them. Okay, so this is something which I discussed yesterday also. This is the nuclear modification factor, and we saw that the nuclear modification factor is way below 1 for charge hadrons and all that. So this gave the first hint about the PT loss, or the loss of energy of the particles when they travel through the medium, and that is reflected in the RIA. So RIA is quite less than 1, that indicates towards the final state energy loss. Then another jet quenching, let's say measurement not involving jets, was to see the dihadron delta phi distribution of let's say correlations between particles. So dihadron correlation. So what you see here, it's one of the very important results which came out of RIC or star experiment, let's say indicating towards jet quenching. But remember here the jets which we discussed were not involved. So you have hadrons emitted all around. So you select, you take two hadrons, calculate their delta phi or the azimuthal angle difference, and you just plot them. So you see, so you have two systems here, PP and goal. So in PP collisions you see, and there is, okay, in PP collisions then goal central, and there is also goal peripheral. So you see for PP collisions, you have the peaks at jet, or let's say hadron dihadrons at phi, where these jets are very close together in phi space. But for the particles which have like a difference of pi, you see that for PP or goal peripheral, you still see the peak, okay? But for central collisions, the peak is completely absent. That says that because these jets have a surface bias, maybe once the jet passes through the medium, let's say it loses energy and the correlation, and hence we don't see any peak here. So this was one of the indirect evidence of jet quenching. So now people have started to see this jet quenching using jets. So now it is jet array, not the hadronic or let's say charge particle array. So you reconstruct jets in lead-lead collisions, you reconstruct them in PP collisions at similar energies and take the ratio. Here also see that the jet RAA is way below 1, suggesting strong suppression of inclusive high PT jets. Okay, so this is now with jets, and here there's a dependence on the jet cone radius. So if you see that this is a jet, let's say jet constructed with a small radius, and then we have let's say three selection of radii, and then you compare them whether the energy loss dependence has anything to do with your choice of just, let's say, jet radius, and you see that RAA is significantly lower than 1. So there's a high, let's say, strong suppression of, let's say, your jets, which is seen in lead-lead collisions, and that is a strong indication of the effect of the matter created in heavy ion collisions, which is not there in PP. Now let's go towards dijet and their asymmetry. So dijets, as the name suggests, these are two jets back to back. So if you see, this is the even display of jets. So if I select, so here you can see is the jets in PP. So just by your, let's say, eyeball movement, you can see there can be 1, 2, 3, 4 or 5 jets, but there is one jet which looks like back to back. Okay, so if you see in the calorimeter or your, let's say, tracking device, it looks like this. Okay, so one is the leading jet. So here the momentum and the, let's say, eta phi coordinates are giving. The other one, or the, so because when you define, I'll tell you how they define dijet. So the thing is that they has to be back to back in opposite hemispheres, and the delta phi angle between them, or say delta phi angle between them should be, let's say, the differences should be greater than, let's say, pi by 2. Okay, now you have a similar event display in lead-lead. Okay, so these are peripheral events. So what you see, you also get some sort of symmetric dijets. Okay, if you see the back-to-back jets, they are quite symmetric. Okay, now come to central events. Okay, the same energy, same jet reconstruction algorithm. So you see the event display here. So if you choose to see the dijets, so you see there is a huge asymmetry now. Okay, the symmetry which was there in PP collisions is more or less now not seen here. So they're highly asymmetric dijets, and if you go to more central collisions, you even see the disappearance of the, let's say, second partner or the subleading jet. And sometimes these are also interesting events where the subleading dijet also splits in the, as whatever it's seen in the calorimeter tau. So what we see that once you increase the centrality, that means the probability of having a very dense medium is there in central collisions, then you see that they are affecting the jets. Jets are getting affected, specifically these dijets, and we want to quantify this asymmetry by an observable known as dijet asymmetry. So it basically, it's nothing that it tries to quantify the imbalance, dijet imbalance, what you saw in detector or in calorimeters. It wants to give a quantitative definition, and we call it dijet asymmetry. It's nothing but the difference of energies of the leading jet and the subleading jet. So when I say subleading jet, it means that the jets are required to have, leading jet will have a certain, let's say, transverse momentum, but both the jets should have energy greater than 20 GeV per C, but sorry, momentum greater than 20 GeV per C, but it also depends on the experiment. The minimum should be, let's say, 20 or 30 for the subleading jet, and this delta phi minus phi should be less than pi by 2. So you can define dijets in terms of energy or in terms of momentum. So both of them essentially reflects towards the same physics phenomena. Now Atlas was the first one to publish the centrality dependence of dijet energy imbalance at LHC energies. So let's see what the figure tells us. So on x-axis you have the dijet asymmetry observable AJ, and on y-axis you have the, let's say, number. So it is the distribution of AJ. Now, if the symmetry is there, like what you see, what you saw in PP collisions and peripheral lead-lead collisions, so your dye-jet symmetry should be near 0 value, correct? So if these two are comparable, right, so the numerator will be less or towards 0, okay? So dye-jet's value should be 0. Now you have comparison for two systems, let's say lead-lead, and the open circles are PP collisions, and then these are the Hyging plus Pythia, that is Pythia jet events are embedded inside the Hyging, which gives you the, let's say, heavy ion background, okay? So what you see here that for and this is as you go from peripheral collisions to central collisions. So as you move from peripheral to central collisions, for PP doesn't make any sense, it's the same measurement, it is peripheral to central for lead-lead. So for PP collisions, let's see that it is expected behavior. So most of the, let's say, events or the distribution is around, let's say, 0. So it's very low values, and that is expected because you are seeing that also in your detector. Now for lead-lead collisions, you see as you move towards higher centrality, like as you move from peripheral events to central events, the dye-jet asymmetry, let's say, it increases, right? So here it is similar to PP, then for 20 to 40 it starts shifting, and in 10 to 20, which is like semi-central, the shift is more, and for central collisions, you see altogether a different peak. So this is the first measurement of centrality dependence, and also it tells us that once and it's a clear evidence showing that once the dye jet or the second part of the jet passes through the medium, so it loses energy, and hence you have this numerator increasing because of this imbalance, and it is reflected in the experimental results. So this was the first measurement at LHC for dye-jet asymmetry. Then this was done in energy because the data was fetched from calorimeter. Then you have dye-jet momentum imbalance, which was measured by CMS experiment. It's a complementary measurement. Here also they see similar behavior. So you have comparison, and see here they mention what are the PT of the leading jets and the PT of the subleading jets. So the rule is that you take the PT of subleading jets to be greater than 20 or 30, whatever you can measure in your analysis. And here they have the Pythia jets embedded in high jet background. This gives you the heavy ion background. So here also see as you go from peripheral to central collisions, the dye-jet asymmetry increases for lead-lead collisions. So this is a strong evidence. So this is a symmetric jet. So here the values of dye-jet symmetry would be very low, close to 0. And this is where you can clearly see the asymmetry. So the asymmetry values are higher. So this is a clear evidence of pattern energy loss, which is observed as a pronounced dye-jet energy imbalance in central lead-lead collisions. Okay, so this was a clear evidence for the jet quenching, what we were discussing. So now another way of seeing this imbalance is to see in terms of this ratio, where the ratio is the PT of the subleading jet with the average PT of the leading jet. So this is also a clear way of seeing the same thing what we saw in the previous slide. So on x-axis we have this PT of the leading jet, and on y-axis we have the ratio. Here we can see that the energy imbalance increases with centrality. So you see this going from peripheral to central events, and you see how the value changes. Because the leading PT of the subjet decreases, hence here the value decreases from peripheral to central collisions. This is another way of, let's say, displaying the same result. Now let's see, when we are seeing this imbalance, then if there is any shift in the delta phi distribution, okay. So this was also first reported by Atlas, that whether the delta phi distribution changes with centrality or not. So more or less the change is not seen, but we see a little bit of deviation for central events, but that is not strong enough to make any sense, make any statement. So the idea is that the delta phi distributions more or less stays similar. That means jets are mostly back to back, but that is also expected because that's how you choose your dijets. Here also CMS also reports a similar result, no apparent modification in the dijet delta phi distribution for different jet PT. Okay, all the jets are still back to back. The only difference you see in the let's say only difference you see that the imbalance increases or shifts more towards the central collisions. Now where do that energy go? So people then try to understand that if you are seeing that imbalance, we should also worry about how to understand where did that energy go. Okay, so what CMS did, they tried to, so whether we are losing, because your jet definition depends upon what R you choose, right? So you are also, because of your choice of R, because of your choice of, let's say, minimum PT, you are also rejecting rejecting most of the particles in the event. So whether you can recover that imbalance from those particles or not. So the idea is that you take a greater acceptance for PT and eta and then project all the particles in the event to the jet axis. So you have your jet defined, then you will have also particles outside that jet cone, okay, which didn't participate in your jet definition. Then you project all those tracks in the event to the jet axis, okay. So you have a jet axis here, so all the particles here, so delta phi, you take the cos of that difference and that will be the projection onto the jet axis, and you try to see whether you can recover the loss or you can explain the imbalance. Okay, so the left hand side shows the asymmetry. On x-axis you have the asymmetry and on y-axis you have this missing, let's say missing PT or the missing energy. And we see that once we include all the particles, you see all the data points, the black points are all around 0. That means we can understand or we could recover the imbalance because now there is no imbalance. So minus sign is towards the leading jet and plus sign is towards the subleading jet. That's a convention. So the upper plot shows the simulation results from PT and high jet, while the lower bottom plots show for real data, real CMS